Oh, we're back looking at problem 83. So here we have vector u. It is 900 representing the kilometers per hour times the cosine of 148i plus sine 148j. That comes from our diagram there, and they give us the angles made with the x-axis on the negative side of 32 degrees, as well as the angle. And using that, we can subtract from 180. Vector v, we can write in a similar manner, 100 kilometers per hour, and also using its angle of 45 degrees, which is given to us in the diagram. So finding the resultant u plus v, we simply add those two vectors together, and you get negative 692.53i plus 547.64j. Using the arc tangent to find theta. Okay, again, thinking about this as being cosine theta, sine theta. So we can think of this as being inverse tangent. You get negative 38.34 degrees. So the direction of the plane is 38.34 degrees north of west. Magnitude of u plus v is 882.9 kilometers per hour. So that's our speed of the plane. 11.2, number 69, I didn't put any work here. We're asked to show that we're looking at a parallelogram here, I believe. Let me just double check that. It's the drawback of taking too long to record these, is I forget what I was doing when I was doing the problem initially. So yeah, on number 69, we're given 4 vertices. We're asked to show that they are indeed vertices of a parallelogram. We got lots of ways to do that. So again, you could use the fact that parallelograms, their opposite sides are parallel, and we have a way of talking about parallel vectors. You could use the fact that their opposite sides are congruent. We have a way of talking about that as well. And so you really could choose anything there. 11.2, number 83. Here we are asked, kind of similar to what we were asked in 11.1. We're given a vector u, vector 0, 3, 3, and we're given a magnitude of some other vector v, in this case magnitude of 10. And we want the vector v to have a magnitude of 10 but still be in the direction of u. So thinking about the fact that we can lengthen the vector u, currently if we use length, it's square root of 18. We can multiply that vector by anything we want so that it maintains its direction, but its length changes. So I chose to multiply by 10 over the square root of 18. Again, dividing by square root of 18 technically turns it into a unit vector, and then multiplying by 10 stretches it back out to being a vector with a magnitude of 10. Doing that, we get the following result there, and I did not rationalize. Number 91. We have vectors u equal to I plus j, vector v equal to j plus k, and vector w equal to au plus bv. And we're asked to do a few things. First, we're asked to sketch u and v. So we have the sketch there. Second, we are asked to, if w equals 0, we want to show that a and b must both be 0. So, all right, I'll assume w is 0. And w is also given to us as au plus bv. So au plus bv then is equal to a times u plus b times v. That gives us the following for the vector w. But again, it's equal to 0, 0, 0 in this case. So we have the following correspondences. A must be 0. B must be 0. Okay, A plus B must also be 0, of course. All right, so then we got to be 0. C, we are asked to find A and B such that W is equal to I plus 2J plus K. So again, we already found that AU plus BV, which is the definition of vector W, we found this in the previous problem that it's equal to A plus B, B. So I'm just reusing that. But if we want it to be equal to I plus 2J plus K, then of course that written in component form would be 1, 2, 1. And so that would mean we need A to be equal to 1, B to be equal to 1, and then of course A plus B would be equal to 2 in that case, making it true. Part D, we're asked to show that no choice of A and B yields vector W to be I plus 2J plus 3K. So kind of similar manner, we're going to write the component form of I plus 2J plus 3K. So 1, 2, 3. Using our other name for vector W, which we've been using in the previous problems, what we would have are the following correspondences. A should be equal to 1. B should be equal to 3. And that A plus B should be equal to 2. But A plus B equals 2, that's impossible if A and B are both the values that they must be. And so it's impossible. 11.2, number 103. We're asked to find the tension in each of the supporting cables in the figure that's given in problem 103 when the weight of the crate is 500 newtons. Alrighty, so we have here, we have 3 supporting cables, and so we're writing the vector for each of those. And of course, the resultant here is the sum of those. All right. The first vector there in component form is 0, 70, 115. And thinking of it as a force where the C1 being this constant for its magnitude, if you will, we can distribute that out. Doing the same with vector AC and vector AD, doing all the same things. We have the following expressions for F1, F2, and F3. All right, when we sum those up, we know that the load is completely on the vertical support. That weight is going down, but these cables are supporting upward. Okay, so it's 500 there for representing that, but zeros for the X and Y direction. All right. So this gives us a system of equations here, namely that when we add up the X components of F1, F2, and F3, we should get 0. Also, when we add up the Y components for F1, F2, and F3, we should get 0. And when we add up the Z components, of course, we should get 500. We solve that system of equations using your favorite way to do that, and you get the following values for C1, C2, and C3. When you plug those values back in, C1, C2, and C3 goes back into F1, F2, and F3. You find the magnitudes as follows: 202.9 newtons for F1, magnitude of F2 is 157.9, and magnitude of F3 is 226.521 newtons.